Hello! So, welcome to our first new format lesson of remote learning. So the idea is that you watch this video, you pause it, you take the notes, etc., everything you need to do, and then we'll work through the questions together on Zoom. So first thing I'd like you to do is have a little think about how a wind turbine works. Can you think of any physics that is connected to it? Anything at all from GCSE or outside that you know how it would work? Okay, so hopefully when you've done that, you start thinking about the different types of energy and the idea that the wind is providing kinetic energy, which is going to turn the turbine, and the turbine would be connected to what's called a generator. And you might remember that from GCSE. And the generator is what turns the kinetic energy into electrical energy, effectively. And how we do that is through a process called electromagnetic induction, which you did do in GCSE, but we're going to redo here, and no real surprise, there's going to be a few equations thrown in as well. So let's crack on. The title today is electromagnetic induction. It is obviously not the 3rd of July 2019, so if you can please write today's date, whatever date that may be, 12th possibly, and let's go. So first bit, basic bit about electromagnetic induction. It's the term used to create electricity in a wire. And we do that by moving a magnet inside a coil. Now there are several things there that you need to know. Moving the magnet is very, very important. Well, I say moving. The reason you want to move it is you want to be changing that magnetic field. If you just put a magnet inside a coil, nothing happens. But if you move a magnet in and out of a coil, you generate that current. Now there's also a key word there that I've highlighted in blue, which is induced. So if a magnet is moved inside a coil, an electric current is induced. Please try and use that word as much as possible in this topic. They like induction. This is because the magnetic field around the coil is changing. And then I've put a phrase here that we used in GCSE. The coil cuts through the lines of the field. Now that doesn't mean very much, but we will go a little bit more into detail later on. So again, if you can please jot that down and then we'll move on. So the next bit we are going to look at are generators and dynamos. Now good news, if you remember in GCSE, you did a lot about generators versus dynamos, AC versus DC, slip ring versus split ring. Good news, you don't need to know any of that in A level. They do not care about the actual parts of a generator. Instead, they want you to know why it generates electricity and how to increase it and things like that. So yeah, in that case, we're looking more at the mechanics than we are at the details. So a generator works by rotating a coil in a magnetic field or rotating a magnet in a coil. It produces an alternating current. And you can see at the bottom there are two diagrams. One showing a slow rotating generator, and you've got infrequent peaks there, they're quite spaced out. You've also got quite a low amplitude, so a low voltage being created. On the right hand side, you have the same generator being rotated more quickly. Now two things to note here. Firstly, yes, the peaks are closer together, they have a higher frequency, but also they create a higher voltage. So the speed not only increases the frequency, but also increases the amplitude, the maximum voltage you get out there. Okay, now let's go on to the A-level bit, the bit that you haven't really covered before, and this is something called magnetic flux. Now, electromotive force, which sounds, I know, very much like the EMF that we do in electricity in terms of energy being given to electrons, but is induced when there is a change in magnetic flux. Now, you've heard the phrase magnetic flux density before, and now we're looking at something slightly different because you know how they like to be similar, same but different. Magnetic flux, and you can see there, I think it's an omega symbol. No, it can't be an omega symbol. Phi, is it phi? P-H-I? Right, apologies, whilst you are looking at this guy. Phi capital. I'm Googling it as we speak. Phi capital symbol, come on. Yes, it is. Okay, well done me. I should trust myself. So magnetic flux, phi, is the product of the cross-sectional area and the component of the magnetic flux density perpendicular to the area. It is measured in Weber. And notice I'm calling it Weber as opposed to Weber because it was a German, I think, scientist. So the W is pronounced like a V. So what this actually means, you've got a lovely equation down the bottom there, is a magnetic field is produced. So you've got a bog standard magnet, fine, it produces a magnetic field. We know that that magnetic field will have a direction. Now I want to produce electricity from that field using my coil, for example. There are two things I need to know about the field in order to find out basically how much of the field is going through that coil. So the first thing I want to know is the angle I've got my coil to the field, because as you know, if it's at a right angle, fantastic, you get a lovely amount of field going through it. But if it's parallel to the field, you don't get any going through it. So the angle is very important. So you see that B cos theta. What you're doing there is saying, okay, fine, you've got a general amount of magnetic flux density. How much is at the right angle for us to use? So that's that. Times the cross-sectional area. Now, what that refers to is the cross-sectional area of whatever conductor you are trying to create electricity in. So if it's a coil, what's the cross-sectional area of your coil? If it's a wire, what's the cross-sectional area of your wire? So what you're effectively saying is, okay, how much of the magnetic flux density are we able to almost capture? That's what that equation is. So magnetic flux is basically the amount of magnetic flux density, which is a general description, are you able to capture? I hope that makes sense on that one. So the last thing we are going to look at, so EMF is induced when there is a change in magnetic flux. So bear in mind, if I want to make electricity, EMF, I can change B, which is our magnetic flux density. So I might have a magnet, like keep on swapping the magnet out for a weaker one or move the magnet away. I could change theta, which is the angle, obviously, that the coil is at, hence why rotating a coil or rotating a magnet creates electricity. Or I could change the area of the coil that we're looking at. So final thing we need to see is magnetic flux linkage, and I'm very, very sorry that all of these have the same names. It was not me who named them. The product of the number of turns in the coil N and magnetic flux. So there you can see magnetic flux linkage equals N phi. It is measured in either Weber or Weber turns. You will not be penalised for whichever one you use. So just a final reminder, and I've put it in bold there, EMF is induced when there is a change in magnetic flux. No change, no EMF produced. Okay, we are going to go do some questions on page 195, but if you can please join me on Zoom once you've got these notes, and we can just work through them together. All right, thanks everyone, I'll see you soon.